This module is about logic optimizations. Let's get started with the logic optimization. So in digital logic, we know there are two types of logic, namely combinational logic and sequential logic. Here we are seeing about combinational logic optimization. So first of all, the question arises, why combinational logic optimization? It's mainly to squeeze the logic to get the most optimized design. The most optimized design will be efficient in terms of area and power. And what are the techniques used for combinational logic optimization? The most basic thing is constant propagation, which is a direct optimization technique. And apart from that, there is a Boolean logic optimization, that is given a very big Boolean logic expression. It can be um, optimized into a more efficient, simplified Boolean logic expression using techniques like K-map or Queen-Minkowski algorithms. So this is one example we are going to look at for a constant propagation. Let's evaluate this. Say for example, if you see here, this logic over here, this is an AND or invert gate. So effectively the equation here is y gets A and B odd with C the whole bar. So this AND or invert gate. Now let's say for example, I have tied low. The A pin is grounded. Now this becomes B and 0, which makes this as 0. Now C or 0 is C, and invert of this will become C bar. So effectively this whole logic is transformed into just an inverter. Now what advantage it gives? Let's say for example, I want to realize this function called y is equal to AB plus C the whole bar. Now let us try to realize this. In terms of CMOS, if I try to realize this, this is correct. So this is going to be A, this is going to be B plus C bar. So of course I'm going to have the dual of this network sitting here. So correct. This is going to be VDD. Correct. And this is going to be my Y. So this is AB plus C the whole bar, and the pull-up network using PMOS is going to be exactly the dual of the NMOS. So A and B are in series. So A and B are in parallel. The series combination of AB is in parallel to C. The series parallel combination of AB is in series to C. So this is the entirely dual pull-up network. So this is the equation for Y realized in terms of CMOS gates. So how many transistors are there? We have 1, 2, 3, 4, 5, 6. 6 transistors, 6 MOS transistors. Correct. Now if I simplify this, I'm getting an inverter. The inverter is going to be just simply this. Correct. So this is 2 transistors, 2 MOS transistors. So definitely 2 MOS transistors is going to occupy less area and it's going to consume less power compared to 6 MOS transistors. So this is an example of constant propagation and optimization due to constant propagation. Okay, that is effectively the constant 0 on A got propagated down the logic downstream and it gave us the most optimized logic realization. Okay, let us look at Boolean logic optimization. In case of Boolean logic optimization, I'm having this expression, say assign y is equal to, so this ternary operator is something like a mux, right? So let's see what it does. So it is looking for the value of A as 0 or 1. If A is 0, if A is 0, if A is 1, it is going to take this, else it is going to take this value. Correct? So if A is going to be 0, it's taking the value of C bar. If A is 1, it is going to look at this expression. Now what is this expression? It is looking at the value of B. Now it's looking at the value of b. If b is 1, it is assigning c. If b is 0, it is looking at another mux for which the select input is c, and if c is 1, it's going to pick the value of a. If c is 0, it's going to pick a value of 0. So this is the expression for y. Now clearly this is the expression for y, but this is not definitely the most optimized expression for y, correct? So let's try to optimize it now. Now what is the equation of this? Correct? So this is nothing but just AC, correct? Correct? The output of this mux is AC plus C bar dot 0, which is nothing but AC. This is the output of this mux. So this is AC. Now the output of this mux is going to be what? It's going to be B bar AC plus B times C, correct? That's the equation of the 2 cross 1 mux, correct? And now what is the output of this y? Now y is going to be A bar C bar plus A times BC plus B bar AC. So upon further simplification, this gives me A bar C bar plus ABC plus A ANDed with this is going to give me same expression because A is already present. So A B bar C. Now AC is common between these two expressions. If I take AC common, I'll get B plus B bar. Effectively, I am sort of doing the K-map without actually drawing the K-map. This is exactly what K-map does, right? So B plus B bar is always 1. So effectively, it turns out to be A bar C bar plus AC. So, or this is nothing but Y is A exclusive or C. That's it. This is the most simplified. So such a complicated expression like this is now optimized into such a simplified expression like this. Correct? So this is also, there's also a constant propagation happening here and also a Boolean logic simplification and K-map reduction, sort of K-map reduction happening here. Okay. So these are examples of Boolean logic optimization. So synthesis tool does these type of Boolean logic optimization to get the most optimized logic. Okay.